Hello all. So in this video, we're going to be looking at exponential functions. So let me share my screen. All right. So we have seen different power functions of x, like x squared, x cubed, square root of x, and so on. But now let's look at a function y is equal to 3 to the power x. Now I've mapped out different combinations of x and y for this particular function. And I have x values running from -4 to +4 and the corresponding y values. And I'm plotting them in this chart. Now notice that when x is less than 0, this function is having really small values. And when x is 0, y is just 1. Now notice what starts happening when x starts increasing. When x is 1, y is 3. When x is 2, y is 9. And when x is 3, y is 27. And when x is 4, it shoots up and goes up to 81. Now, this is a pretty dramatic looking graph. And this is an example of an exponential function. So if there is something that is increasing or decreasing by a constant factor, then it's said to be either increasing or decreasing exponentially. And oftentimes when we draw functions of this type, or when we're trying to understand what's going on here, the x is usually measured in units of time. So we're looking at things which will increase or decrease by a factor per unit of time. And we tend to see exponential functions in several applications of economics. And let's learn more about this function. Now, as I mentioned, a quantity that increases or decreases by a fixed factor per unit of time is said to increase or decrease exponentially. And the general exponential function with the base small a is written using this formula. And capital A is just a constant. And you have a number a raised to the power x. Notice here that your x appears in the exponent, and hence the name exponential function. Now, small a refers to the factor by which f of x is changing when x increases by 1 unit. Now, generally, exponential functions have the property that this factor by which something is increasing or decreasing is a positive number. Okay, and this will make much more sense when we look at a few examples. Now, Now, I mentioned earlier that x is usually measured in units of time. And if f of t, so to say that it's a function of time, f of t is given by this expression, capital A, small a to the power t. And this is the value of the function at time t. Now, if time changes by 1 unit, which is, let's say time is increasing by 1 unit, t plus 1, the expression becomes a to the power t plus 1, which is nothing but a to the power t multiplied by another a. It's just f of t times a. So you see how f of t plus 1, so we have f of t plus 1 is equal to f of t times a. So when your time changes by 1 unit, your function is changing by a factor a. And that's the key property of the exponential function, which makes it look the way it does. Now, what I've graphed out here are the general shapes of the function when the factor of change is greater than 1 and between 0 and 1. When it's greater than 1 is where you see the blowing up phenomenon of something like 3 power x or 2 power x. It's just going to, starts off once it crosses that x is equal to 0 threshold, it blows up. So that's the general form of the function when a is greater than 1. And when a is a fraction between 0 and 1, your function takes the form of something that looks like a hyperbola. Okay, let me correct that. Something that just looks downward sloping this way, okay? And this, the left panel here is often referred to as exponential growth because it's something that's blowing up. Whereas on the one on the right-hand side is something called an exponential decay. If something is increasing by a factor of just say half. So if something was 300 today, then tomorrow it's going to be just half of that, it's going to be 150. And then the next day it's going to be 75 and so on. That's called exponential decay. Okay, I'm just going to put those two phrases here so that you're familiar, but we don't have to worry much more about it at this point. Now, where do we see exponential functions in vogue? We see them when we talk about economic growth, population growth, especially compound interest cases. So now let me give you a simple example. So you invest $3,800 in a savings account today in year 0, and the bank pays 1.8% interest rate on the money every year. Now, how much money will the account hold in 15 years? Now let's work it out. In year 0, we have $3,800. At the end of year 1, we're going to have the money that we invested plus 1.8%, which is just 0.18, and 1.8% of the money we invested, which is given by this expression. And so collecting terms, we can write 3,800 into 1.18. In year 2, we start off with this money, and we're going to get an interest of 0.18% on the money that we have. In collecting terms again, we end up with this. Now you start seeing the pattern here, right? 3,800, and at year 1 you multiply by 1.18, year 2, 1.18 squared, and so on and so forth. At the end of year 15, you're going to end up with this amount. And this is roughly, I think, about, this is about $45,000, if I'm right. So you start off with 3,800, and in 15 years, you end up with some $45,000 without doing anything. It's just the interest which keeps compounding. And that's the exponential function in full display. Now, I have another example here, which shows you the difference between linear growth, which is changed by a constant amount. This is exponential growth, which is changed by a constant factor. Go through this example, and this is another illustration of the power of compounding or power of exponential growth. So there are two companies which offer a certain monthly payment. Company A starts off at 10,000 and promises to increase the amount by 5,000 every month. So the amount changes by a constant amount every month. So every month it increases by 5,000. Whereas company B starts at $500 and tells you that it will double the pay every month. So you go from 500 to 1,000 to 2,000 to 4,000 and so on. We want to find out for which monthly payment is company B's pay greater than A's pay. So I've written out the table here, mapping the monthly payment for each month. And then for A, you see how the amount increases by 5,000 every month. Whereas for B, the amount doubles. So if you take any two consecutive numbers, the ratio between them is going to be the same factor. So here, it's constantly 2. And at the end of the 8th month, company B's payment overshoots A's payment. And this is another illustration of the exponential function in display in full force. Now, so we have this is the general form of the exponential function. And each base A will give us a different exponential function. 2 power x, 3 power x, 1 by 2 to the power x, and so on. Now, an important base that one would often see in economics is something to the base E. Now, E is an irrational number which expands, which is approximated by 2.71828, and that's called E. It's called the natural exponent. Okay? And when your exponential function has E as the base, then you can write it out as f of x e power x, and it's the natural exponential function. Okay? And the same algebraic rules that we saw earlier for other variables also apply to e power x. which is what I've illustrated here. And I've drawn the graphs of e power x here. Now e power 0 is 1. Just like how a power 0 is 1 as long as a is not 0. Similarly, e power 0 is also 1. And that's the line you see. And this is e, and so on. So this is the graph of y e power x. And on the other side, I've plotted the graph of 1 by e power x, or e to the power minus x. And that's just, it's just reflected about the y-axis. And now what's interesting about these exponential functions, and what's one factor that is really important and we'd like to know more about? Now, if I write the exponential function as a function of time t, then I can look at how much time it takes for a particular value to double. Now, if say at time t is equal to 0, I start off with f of 0, and that's just a. Now, if I'm interested in how much time it takes for something to double, I can express that using the exponential function. Now, f of t star, I want to find the time t star such that I move from a to 2a. And I plug in the exponential function value for t star, and this is the expression, and that is equal to 2a, which lets me stop at an equation where a t star is 2. Now, how do you find t star? That's the topic for the next video. See you there.